Anybody want to chat for a few minutes about our math chat question? I don't know if does anyone find this question interesting? Is there a limit to what math can explain? Anybody have feelings about this? In my other class, we had little, discussion groups and all that. I don't think we need to get into that because I do have stuff I want to talk about for today. Anybody? Anyone think the answer is no? Math can explain everything, or there are some things that math can't explain. Math can explain how to do the quiz right. Yeah. Nobody wants to offer an opinion. I feel like my gut reaction to this question is actually in my real life, in my ordinary life, of the things that I truly care about, math is almost no help at all. Math, knowing, I have a PhD in mathematics, but this doesn't help me love my kids more, or have a good marriage, or live a good and fulfilling life in the way that I want to live my life. To me, math is not I think there's some kind of Hollywood idea that a mathematician sort of sees the world in a special way. When I look at things, I see little equations flying everywhere. But this is, I don't know anybody like that. I mean, to me, mathematics is not a good framework through which to view the world. I mean, if you're doing science or doing math, then absolutely mathematics is the proper framework to do those things. But in terms of, to me, as a normal human being, doing the things in life which are important to me, math doesn't help me do that. Other than, one of the things that's important to me is to have a career and be good at something that I enjoy. And math is something that I'm good at and I enjoy, and it is my career. So in that sense, math is important to me personally in that way. But it's not, I don't use it as the language through which I express my existence or anything like that. Any thoughts about that? I'm just telling you my own opinions, but I don't claim that my opinions are any more interesting than anybody else's. Every so often, I do have things in my life that work as sort of a guiding principles or a framework, but they are not derived in my mind mathematically. Every so often I meet someone who is an extreme atheist maybe, and it's fine to be an atheist, but sometimes I meet someone who's I'm an atheist or whatever because I can't believe anything. I'm not going to believe anything unless you can prove it to me. And I kind of get that as a general principle, I do believe people shouldn't believe things just for no reason. But mathematical proof, is an extremely high standard in my opinion that I don't actually apply to almost anything in my real life. I believe that my wife loves me, but I'm not able to prove that. Certainly not mathematically. I can't even formulate that to begin with as a mathematical thing, which I might want to prove. So ordinary things in my real life, I do not expect to apply mathematics to them. And that's totally fine. So in that sense, I actually am very comfortable believing things that I can't prove, because I prove almost nothing about anything in real life. I prove things in math. And I don't believe things in math that I can't prove. But things in ordinary life, proof is not the standard for me. I mean, it's something like that. I don't believe things for no reason at all, but it's not about proof for me. Any other thoughts? I don't mean to just monologue here. One other thing that I can say about this. The other thing that comes to my mind when this question is posed to me is actually, maybe this is a question about mathematics itself. Are there actual limits to mathematics on the whole? Within mathematics. And the answer to that question, surprisingly, I don't know if you ever thought about this. The answer is actually yes. So in math, I will write this down because it's so important. In math, there are what we now call undecidable propositions. Most of mathematical research is about trying to prove new theorems, which are true things that you try to prove. And if somebody approaches you with an alleged theorem, is like, do you think that this is true or not? The reaction, or like what mathematicians do is you try to prove that it's true, or if you think it's not true, you try to prove that it's not true. All right, but actually, there is such a thing as what we call undecidable propositions, and these are things. I'll give you an example. One is called the continuum hypothesis. I don't know if you've heard of this. Continuum hypothesis. This was viewed at the beginning of the 20th century. This was viewed as one of the most important unsolved problems in mathematics. And it's a specific statement about different sizes of infinity. There are actually different sizes of infinity. And there are a lot of mathematicians who study this. This is referred to as transfinite numbers, transfinite mathematics, which is about numbers which represent different sizes of infinity. But anyway, the continuum hypothesis was a specific question about different sizes of infinity, and people for a long time were trying to prove that the continuum hypothesis is true, or maybe you try and prove that it's false. Either way is a satisfying resolution. It turns out, to everyone's surprise, like around the 1960s, it was actually proved that this is provably unprovable. That means somebody proved that there can be no proof one way or the other of the continuum hypothesis. How do you like that? And so in the sense of like, some people say like mathematics is all about trying to determine what things are true and what things are not true in like abstract logic. And I wouldn't disagree with that statement, but actually there are some things which are kind of neither. The continuum hypothesis, it might be true or it might not be true, but there can be no logical proof either way. Any thoughts about that? This is really the last thing that I will say. There's an old sort of mathematician joke that's not really funny at all, but it's someone is asked, what's the first thing you're going to say to God when you meet God, when you die and go to heaven? And he says, is the continuum hypothesis true? Because this is a question which we now know is impossible to find the answer to. The only way you're going to get an answer is to ask the good Lord himself. Strange but true. I mean, the stuff about asking God is meant to be a little silly, but it's true. The continuum hypothesis. So nowadays, when people talk about unsolved problems in mathematics, there are theorems that people are trying to prove or trying to disprove. But actually, there's a third option, and that is you can also try to prove that something has no proof. And that is, nowadays, we don't think of everything in terms of true and false. There's true and false and undecidable. Very interesting world we live in. All right. There we go. This actually is one way in which math kind of does impact the way that I see the world. To me, I don't know if this means anything to you, but to me, the existence of such things is actually very meaningful to me in the way that I think about my place in the universe, and even the way that I think about God. I mean, this doesn't prove anything to me one way or the other about God, but just the fact that there are certain logical things which human beings cannot understand one way or the other is interesting to me. Well, all right, let's get back to the calculus then. I actually don't know of any undecidable propositions in calculus, but actually it has been demonstrated that these undecidable statements exist in all areas of mathematics. It's not just this one weird thing about the continuum hypothesis. It is kind of everywhere. Okay, so we're going to talk today about a new section, and this may be new to everybody. I'm not sure that typical like high school. I know some of you have had really good high school math classes. Some of you have not seen much of this at all, and that's fine either way. This I think might be new to everybody, although I'm not sure of that. This our book refers to as trigonometric integrals. This section and the next section are ones which I know I personally never did in high school, and I actually didn't even do them in college. Trigonometric integrals. So this is about integrating powers of sine and cosine. Everybody knows, of course, the integral of sine x is minus cosine x plus c. The integral of cosine is sine. And in fact, for this section, it will be helpful to just straight up remember, I will say, and if you have, this is not hard to work through the details on your own. If there's an extra constant in there, sine of kx, where k is a constant, so it could be like sine of 3x or something, how you would handle that is I would do a u substitution, u equals kx, and then do a fairly straightforward thing, actually very much like what appeared on the quiz today. The result would be 1 over k, well, it's negative because of the cosine.
Isn't it just sine goes to cosine, cosine is negative sine? Like for the, oh, that's the integrals.
Yeah, these are the integrals, yeah.
Okay.
So when you do it with an extra constant on the inside, this is the effect. You get this extra 1 over constant in the front. That's because it comes about by doing the u substitution and like dividing by the constant to match up the du. And then similarly with the cosine kx dx is 1 over k sine of kx plus c. So this is worth remembering. It's just a slight variation on the ones up there because these will come up every so often when you're doing the more complicated integrals that we're going to talk about in this section. So the tricks that we're going to use, I want to try to do things like something like integral cosine to the 4x sine cubed x dx. This is the kind of thing that we're going to talk about doing in this section. So looking at that, my initial reaction is maybe I should do parts here just because there are two things that are being multiplied by one another. And that's the typical scenario when you use integration by parts. But I also begin to think about doing some kind of substitution because this is like sine of x, the whole thing cubed. And this is like cosine of x, the whole thing to the 4th power. And that's usually I would try to do a u substitution when there's like a thing inside of a power or something. But the fact that there's two of these means none of those tricks by themselves will work. So you can't directly do this with parts, and you also can't do a simple u substitution here. And so the tricks that we're going to use are based on some somewhat obscure formulas. Well, this first one is not obscure. It is sine squared x plus cosine squared x equal 1. Everybody knows that. But there are other formulas for sines and cosines of things like there's like the angle addition formula, sine of a plus b equals blah, 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 some stuff that you probably learned at some point. I don't really care if you know that one that I just said, but there are two that will be useful in this particular section. One is sine squared of x is 1/2 1 minus cosine 2x. This comes from the formula for, there's a formula for cosine 2x. It's one of those angle addition formulas. And if you rearrange that formula and solve it for sine squared, it looks like this. It's probably not the way that you learned this formula if you ever did, but this is equivalent to that. And then there's another one for cosine squared, and it's almost the same. It is this 1/2 1 plus cosine 2x. All right, so these are two formulas, and it really is cosine both times there. These are two formulas that I would say in general are not terribly useful formulas, but we're going to use them in this section. All right. And the tricks to do involve some combination of u substitutions and these formulas here. So I want to do let's do one example. I have a couple, and then I have one for you to try. Let's try integral of cosine cubed x dx. Of course, this means cosine of x cubed, right? to me, I don't really like writing it the first way. The second way is much clearer in my opinion. Cosine of x cubed. Now, when I see this, like I said before, when I see this, my initial idea would be to do a u substitution where u equals cosine x, and then this turns into u cubed. Can anyone say the problem with that? That actually won't work in this case, yeah?
There's nothing to like cancel out when you do like a du.
Yeah, the du, what I want for the du is not present here. So you don't have to write this down because it's not going anywhere, but my idea would be this, and then du is sine x dx, negative sine x, because that's the derivative. But so you can make this u cubed, but then there's nowhere here to see a sine x and deal with the dx in that way. All right. So the trick here is instead of that, so I am going to do something like that eventually, but the trick is to kind of make the signs appear sort of out of nowhere. I'm going to save. This is my name for this trick. Our book doesn't call it this, but this is the old save one trick. I'm going to save one cosine. What I mean by that is write it as cosine x squared and then another cosine x. All right? And the cosine squared, I'm going to use the formula that you can see close to the top there. Sorry, not that one. I'm going to use the one about sine squared plus cosine squared equals 1. All right? Save one cosine and then rewrite the other in terms of sine. So the cosine x, that's cosine squared there. I'm going to write that as 1 minus sine squared x. And I have a cosine here. All right? That's because sine squared plus cosine squared equals 1. And if you rearrange that, it means cosine squared equals 1 minus sine squared. All right? You feeling it? I don't know if you're feeling it, but now we can do u substitution. U equals sine of x. I don't know if it's clear that that's actually going to work, but it really is. What's the du then? It's cosine x dx. And then, can anyone say, how do I write that once I do the substitution? Yeah?
Negative on the outside of the. Oh wait, no, sorry, it's the derivative. My fault. Just 1 minus u squared du.
Yeah, great. Isn't that nice? You save one of the cosines, rewrite the others in terms of sine, and the reason you save one of the cosines is so it can become the du when you do this substitution. All right? This is the trick that we're doing here. You save one of the cosines so that it can become the du, and then you do the rest of it as a substitution involving sine. All right? So anyway, can we just finish it off? So this now becomes an easy integral to do. It is now u plus 1/3 u cubed. That's the antiderivative, plus c. And then I put the original variable back in. The answer is sine x plus 1/3 sine of x cubed plus c. Yes?
So why is it plus? Because it should be minus.
Minus, yeah, sorry about that. Those pluses should be minuses. Yes. Give me that. All right, this is the basic trick. Save one of them to become the du, and then the other ones, rewrite them in some way to make it all work out. All right. Let's try one other example. Or I will just try to say again in words what I'm talking about. So this trick works when at least, I'll try to say a little bit about this, when at least one of the exponents is odd. I'm talking about exponents like, generally speaking, what we're trying to do here is something like sine to the n of x times cosine to the k of x. All right? If one of those exponents is odd, You can save one of them, and then they're both even. The rest, after you save one of them, they're both even. And then the even ones you can rearrange and write in terms of all the other variables. So the idea is you save one cosine and write the rest as sine. Or you can do it the other way around. Save one sine and then write the rest as cosine. Either way, this will work. But generally, it only works if one of them is odd. So you take the odd one and save that one. And then the rest of it is all even powers, and you can use that thing about the sine squareds or the cosine squareds. All right? This is the idea. Let's try one more example, and then I got one for you all to try. So I'm going to do sine squared x cosine to the 5th x dx. All right? Like I said, this trick, generally speaking, works when one of the powers is odd, and that's the one you want to save one of. So I'll say the cosine is odd. I mean, that exponent there, the number 5, is an odd number. So I'm going to save a cosine. So what I mean by save is I write this, sine of x squared, and then cosine x to the 4 times another cosine x dx. And my intention is that that cosine x dx becomes the du. So that means my substitution is going to eventually say u equals sine of x. We do need to rewrite this part. All of these guys we want to write in terms of sine. So, I mean, this is already a sine. So really I'm looking at this cosine of x to the 4. And this we have to write in terms of a sine of something. And there's yet another trick to do here to get that to look like sine of something. This is like that. I'm going to say this is cosine squared x squared. And then that cosine squared I can write as a 1 minus sine squared. And that will have changed everything into sine. Everything into sines over here. All right? So if you have an even power on the cosine, you can do this trick, where you turn it into a cosine squared to some other power. And then this cosine squared I write as a 1 minus sine squared. And then hopefully stuff will work out. So this is sine of x squared. Now I have 1 minus sine squared x squared, like that. Cosine x dx. Now this is all in terms of sine, and we can do the substitution. U equals sine x. Du equals cosine x dx. In my opinion, this is a little tricky. It involves using a few sort of random tricks, which can be a little taxing to keep it straight. Anyway, what do we get when I plug the u's in? Someone want to say? It's just every sign turns into a u. What do you think?
U squared times 1 minus u squared squared.
Yeah, great. And? Du. Yeah, excellent. That's what it is. And now, can you do this integral? This is still somewhat complicated as far as integrals go. Anyone have an idea here? Don't say do another u substitution. It's not necessary. Yeah?
Can you distribute?
Yeah, distribute here. I would say how I would describe this is you should do this exponent, like do the FOIL here, which I think is what she meant by distribute. Don't try to distribute directly inside the squared parentheses. That's not allowed. But I'm gonna do u squared, and then maybe you can do this in your head, but I'm just gonna write it all out like that, right? And then do the FOIL here. This is u squared times. The first thing is a 1 times a 1, so that's a 1. On the inside, I have negative u squared. On the outsides, I also have negative u squared, so this is minus 2u squared. And on the end, minus u squared times a minus u squared is a plus u to the 4. All right, and what should we do now? Distribute, yeah. They just keep on telling me to distribute. So now you can just straight up distribute u squared across this whole thing, these three guys. So it's gonna be u squared minus 2u to the 4 plus u to the 6 du. And now this is a polynomial, so we can just do the integral easily. The rest is simple. So this is 1/3 u cubed minus 2 over 5 u to the 5 plus 1 over 7 u to the 7 plus c. And then finally we put the original variable back in, which was u equals sine x. So this is 1/3, if you like, sine cubed x minus 2/5 sine to the 5x plus 1/7 sine to the 7x plus c. That's how we do it. Any questions about that? This is the kind of thing that, like, if you're making a movie about a mathematician, this is the kind of thing you want to see, like on the blackboard while they're talking, doing a little scene. It looks really complicated, and it is kind of complicated. All right, I got one for you all to try. Same kind of tricks. Let's try integral sine cubed x and cosine cubed x. Now this one, they're both odd, so actually you can, it's sort of up to you. Dealer's choice. You can save a cosine and do it that way, or you could save a sine and do it that way. If you save a cosine, it will look very much like the one we just did. If you want to be a little more adventurous, you could try to do it the other way. See what you think. I'll try and scroll up so you can, where we began was too long ago, too far away. You can kind of see that. You should start by pulling out one of the cosines and writing the other ones in terms of sine. Or if you like, you could pull out one of the sines and write the other sines in terms of cosines. Pick one with an odd exponent, but otherwise, like here, they're both odd. Oh, well, for this type of trick, it's always the first one. Oh, okay. Use one of the others. They don't. Yeah, it's not a good idea to use these ones. This type of. Good here. Yeah. it's cosine to the 4, which makes it squared to squared. But you have, yeah, right. It's easier. Yeah, just this, and then this just by itself. Looks like people are doing pretty well with this. Let's see if we can do this. I know not everybody's totally finished, but so I'll do it. I will save one of the cosines just so that it looks most similar to the example we already did. So this is sine cubed x, and then I have cosine squared x times cosine x dx. That cosine squared I write as a 1 minus sine squared. So this is sine cubed, and then 1 minus sine squared x, and then cosine x dx. That 1 minus, and now I do the substitution, right? U equals sine x. Du is cosine x dx. And so this becomes integral u cubed 1 minus u squared du. This is, now the hard part is over. The hard part is really just like keeping straight in your mind which of these tricks to do and in what sequence. Hopefully, if you're just copying one of the answers or one of the examples we just did, it should be fairly straightforward. Now to finish, I distribute u cubed minus u to the 5, and then integrate. This is 1/4 u to the 4 minus 1/6 u to the 6 plus c, 1/4 sine to the 4x minus 1/6 sine to the 6x. Any thoughts about that? This is how we do it, all right? So this is the save one trick, and it works. This trick works if either power is odd. You should do the old save one of them trick. All right? Yes?
I did that with u equals cosine x.
Uh-huh.
And then my answer had cosines.
Yes,
Is that
yeah.
correct?
Yes.
Okay.
If you do it, yeah, if you did it the other way around, you would have had to use the u equals cosine x, and then that means automatically whatever you got is some variation of this, but with like minus signs instead of plus signs or something. But whatever you end up with will have cosines in it instead of sines, and you may worry about, isn't that like really different if the answer is supposed to be sine versus cosine? But it's because of these even powers. Every time you see cosine to the 4, that can actually be rewritten in terms of sine squared and sine to the 4. And so it is, if you did it another way, your answer might look very different, but actually still be correct. Great. Okay, so if either power is odd, do this, what I call the save one trick. All right, what about if both of the powers are even? Then you may have problems making this work. So for even powers, that is like when all the powers are even, this requires a different set of tricks, and this is the ones in which we use those other ones that I wrote before, which I will write again. Sine squared x equals 1/2 1 minus cosine 2x. Cosine squared x equals 1/2 1 plus cosine 2x. All right? You can use these to basically decrease a power by 1. If you have cosine squared, if you don't like the fact that they're all even, you can do this, which exchanges a cosine squared for a cosine. All right? That's why these tricks are helpful in this setting when they're all even. So I think I'll just do an example like that, and then, well, I'll do a couple examples like that, and that'll probably do it for today. Let's try integral sine to the 4x dx. All right. So here we have an even power and no odd power of cosines along with it to save. And so here's how we can use those tricks that you see up there. When it's even, you can do this. All right, sine to the 4. Now, I can't directly use these formulas here because it's sine to the 4, but I can write this as sine squared x to the squared, right? The fourth power is a squared and a squared, and then I can use that formula that you see up there. So this is integral, okay, inside the parentheses I see 1/2 1 minus cosine 2x to the 2, right? All right, can we do anything with that? Yeah, you can do the FOIL here. So I'm going to actually square that out. Now the 1/2, right now the 1/2 is inside the square. So the 1/2 needs to get squared, and then I'm also going to do the FOIL thing. So the 1/2 becomes a 1/4, and you might as well take it all the way out. And then what remains is 1 minus cosine 2x squared, and I'm going to do the FOIL on that. So it'll say 1 minus 2 cosine 2x plus cosine squared 2x. Right. This is a completely different trick from the other one. And actually, this trick is not going to end doing a u substitution. You're just going to use these formulas. Actually, you can use the two formulas you see at the top there. We can apply them yet again. Anybody see how to use those formulas again down here? I know it's late on a Friday afternoon. We already talked about God, though.
At the end of it says cos squared 2x, you can plug it in the bottom.
Yes, I'm going to use the second formula here, cosine squared of x, on that. So using this, but with 2x instead of x, all right? We are using that cosine squared right there, but with 2x instead of x. That means it's going to look like, I'm try and keep that on the screen. It's going to look like 1/4 integral 1 minus 2 cosine 2x plus, all right, here it's going to say the formula up there, 1/2 1 plus cosine 4x. That's because I used the formula, but with 2x plugged in for x. This is a little weird, but actually this is sort of the last of these weird steps that we have to do. Of course, the dx on the end. Now we can pretty much do the integral. Maybe I will first distribute the 1/2 there on those parentheses. So this is a 1/4. I'll big it up again. Integral 1 minus 2 cosine 2x plus 1/2 plus 1/2 cosine 4x dx. And now each of those things, you can just do the integral term by term. It's a bunch of things added together, and each one is, well, some of them are constants, and the other ones are cosine of something x, but I will refresh your memory what I wrote at the very beginning. Integral of cosine kx is 1 over k sine of kx. This is why I said this would come in handy in this section. So where you see cosine 2x, it's going to do the thing in the red box there. All right, so what we get? 1/4. I'm doing the integral now. So 1 becomes x minus 2 cosine 2x is going to be 2 times 1/2 cosine 2x. This 2 is just because there was a 2 there to begin with, and then this 1/2 cosine 2x comes from doing this formula. It should be a sine, sorry. Not cosine. I'm doing the formula in the box. You do the integral, the cosine turns into a sine. Sorry about that. All right, next, plus 1/2 becomes plus 1/2 x, because that's a constant by itself in the integral. It becomes the same constant times x. Next, plus 1/2 cosine 4x becomes 1/2 1/4 sine 4x plus c. The end. That's all there is to it. To me, this is these are kind of tricky. Just it's hard to keep straight all the various tricks that you use from one step to the next. But with some practice, I hope that you will come to remember it without too much trouble. Any questions about that? I got one more to try, but just to make sure.
Do we have to memorize all these formulas, or will they be given for the quiz?
This is something that I have thought deeply about recently, and I'll get back to you. I mean, really, it's so this. Sorry to scroll if anyone's still copying down. Everybody already knows this formula, so really, it's just these two, which to me is not all that egregious if I just tell you to remember these two formulas. Although, like I said, I'm thinking about it. To me, I think what makes it harder is just you have to remember these formulas, and also you have to know when to use each one, which is a little complicated. Basically, if they're all odd, you do the save one trick, which uses only this one, and if they're all even, you do this other trick, which uses only these two. So it's not so bad. You will hopefully get a good feel for it by doing more on the homework. Let's just do one more, and that'll do us for today. How about another one where they're all evens? Integral sine squared x cosine squared x dx. All right. This involves one last initial trick before we sort of get going with the stuff from before. Here they're all even, and you should just immediately use this sine squared x plus cosine squared x equal 1 to make it either all sine or all cosine. All right. You can change the sine squared into a 1 minus cosine squared, or you can change the cosine squared into a 1 minus sine squared, and then it'll all be the same ones. And I don't really care which way around we do it. How about let's change them all into sines? So I'm going to use. So I'll do. Although you could do this the other way around and it would work fine. I'll do cosine squared equals 1 minus sine squared, to change them all into sine. So this is sine squared x times 1 minus sine squared x. And then where I'm going to go from here, first distribute, and then do these sort of those 1/2 formulas to reduce the powers all down to powers of 1. So we're going to do first distribute. Sine squared x times 1 is sine squared x, minus sine squared x times sine squared x is sine to the 4x. And then we're going to use those 1/2 formulas, specifically sine squared x equals 1/2 1 minus cosine 2x. Right. This is the formula that we're going to use several times. So we're just going to do this directly on the first part. This first part just literally becomes that stuff. 1/2 1 minus cosine 2x. That part we already know how to do this integral, right? You could distribute the 1/2, but then it's just you would do each part of that. What to do with sine to the 4? Any thoughts? Yeah?
We can make it sine squared of x squared.
Yeah. Like so. And then what to do with that? That inner sine squared, you again use the 1/2 formula on that. So we got 1/2. Can I distribute the first 1/2 there? It says 1/2 minus 1/2 cosine 2x. And then minus this thing inside the parentheses, I use the 1/2 formula again. And then we are going to do the FOIL. So from here, it looks very similar to the one we just did. Do the FOIL on that squaring over there. The 1/2 will have to turn into a 1/4 because the 1/2 is inside the squaring. So it's a 1/2 minus a 1/2 cosine 2x. That stuff I like just the way it is. Minus a 1/4. Now do the FOIL. Can someone tell me what do you get when you do the FOIL?
1 plus 2 cosine of 2x minus cos squared of 2x.
Great. I think I disagree with the signs you said, but.
Oh, I like distributed the negative.
Are you okay? Great. She's one step ahead of me.
Sorry.
Cosine squared 2x. like so. Right, and then I'm going to distribute the -1/4, which will flip-flop all the signs and also add some fourths. So 1/2 minus 1/2 cosine 2x minus 1/4 plus 2/4 cosine 2x minus 1/4 cosine squared 2x. All right, getting somewhere. The only thing here I don't know how to handle, we're just going to go through left to right and integrate each part. The only thing is this cosine squared. What should we do with that?
Use like the formula again.
Yeah, this 1/2 style formula again, although not this one exactly, it's the one with a plus in it. So this being a cosine squared of 2x, I get 1/2. These are taxing. Even if you know what you're doing, it'll take you a few minutes to work all this out. 2/4 is the same as 1/2, of course. Okay, minus 1/4 cosine squared of 2x is the same as 1/2 1 plus cosine 4x. I think I did that right. Right? And that, after distributing some stuff, we will be ready to actually do the integral. All right, so actually, did you notice in the rest of it, I have here -1/2 cosine 2x and here plus 1/2 cosine 2x. So those can just straight up cancel. We don't have to deal with them anymore. Isn't that cute? And would you mind, can I put together these constants? 1/2 and minus 1/4 makes plus 1/4 when you add them up, right? 1/2 minus 1/4. So I go integral, those constants put together is just 1/4. And then the rest of it, distributing 1/4 on the end, it says 1/8. Maybe I'll write it this way. 1/8 plus 1/8 cosine 4x. But I have to distribute that minus sign also. 1/4 minus 1/8 minus 1/8 cosine 4x. I'm looking at my paper to make sure this is where I should end up. I think so. Anybody disagree? It's very easy to mess up the details while you're doing these, so this is why I'm concerned. All right. Finally, can we do the integral? 1/4 becomes 1/4 x. You could add those constants together before doing the integral if you like. Minus 1/8 becomes minus 1/8 x. And then finally, 1/8 cosine 4x is, using that formula in the red box from before, 1/4 sine 4x. The end. It's pretty involved, I would say. And I think that'll do it. You'll have some practice with these guys on the homeworks.